Hello everyone, welcome to my presentation on implementation of Altera Neos 2 instruction set architecture in Verilog. My name is Pranav and I have taken this course EE 275 under Professor Chang Chu in the summer term. This is my term project. So what are the objectives of this project? The objective is to understand the Altera Neos 2 architecture and understand the concept of pipelining, why we pipeline architecture, and implement a subset of the instruction set architecture of the Neos 2 processor using the Verilog, and verify the Verilog code using three different programs. One is a benchmark dot product program, the other one is the array sum program, and a factorial of a number. So let's quickly have an introduction to the Neos 2 architecture. Neos 2 processor is a soft IP core, which means it's a microprocessor which is fully described in software using a language called HDL, in this case the Verilog, and this can be synthesized in a programmable hardware on a FPGA. So the Neos 2 follows a RISC type of architecture, which is a reduced instruction set computer architecture. It has a 5-stage pipeline configuration and a full 32-bit instruction set, data path and address space, and it has 32 general purpose registers, and each of the registers are 32 bits. So let's quickly have a look at the architecture of the Neos 2 processor. So generally the processor is divided into 5 different stages. As you can see, there is one stage called fetch, then the decode stage, then the execute stage, then the memory access stage, and the write back stage. You can also see the instruction memory in the fetch stage, the data memory in the memory access stage, and the general purpose registers which are in the decode stage. And this is the arithmetic and logical unit, which is the heart of the processor in the execute stage. So let's understand what happens in each pipeline stage. So while you're fetching an instruction, there is a register called program counter, which is used to fetch the next instruction from the instruction memory. So the program counter keeps incrementing and fetches the next instruction to be executed from the instruction memory. Next, the instruction decode stage. So once we get the instruction, which is 32 bits, it is decoded. It has different fields, and the fields are read and decoded, and the type of operation to be performed is determined, and it is accessed from the general purpose register. The next stage is called the execute stage. All the instructions are actually executed in this stage. For memory instructions like a load or store, the base address and the offset addresses are added to obtain the effective memory address to be accessed in this stage. If it is a addition or any logical operation, that is performed in the execute stage. Next is the memory access stage. This stage is for load and store instructions. If you want to load the register from the memory, or if you want to store something from the register to the memory, then memory access stage comes into picture. So the effective address which we calculated in the execute stage is applied to the data memory, and according to the instruction type, a read or a write is performed into the data memory. The next is called the write back stage. So the results of the calculation from the execute stage or the memory access instruction loads from the load instruction is written back to the register in this stage. So two things can happen: either the ALU output or the memory output from the data memory is written back into the general purpose registers in the write back stage. So this shows a quick diagram of a 5-stage pipeline, and what happens cycle by cycle. So during the first clock cycle, the first instruction is fetched, and during the next clock cycle, the second instruction is fetched, and the first instruction is in the decode stage. And when the first instruction moves to execute stage, the second instruction is in the decode stage, and the third instruction is in the fetch stage, and so on. So it takes 5 cycles for the pipeline to fill up, because it is a 5-stage pipeline. And at this juncture, the pipeline is full and it is busy executing different instructions at different stages. So this area is called the pipeline filling, and this area is called the pipeline flushing. So let's look at the simulation results of the program which we ran on the Verilog code. So the first one is the sum of two arrays. So let's say you have two arrays. The number of elements in the array are 8, and these are the two arrays which we have taken. So the expected result is 400, which is the dot product of these two arrays, which is 400 in decimal or 190 in hexadecimal. So this shows a part of the instruction code. So the instructions here have been rearranged in order to get rid of hazards. So I'll show you what is hazard in a moment. So when we run this instruction on the Verilog simulator, we get a waveform something like this. So the first clock cycle, is reset, where all the registers are reset and the PC and instruction, everything is reset. And the next instruction is 4 because the PC increments by 4. And the instruction which is to be executed is given in this register. So as you can see, the PC increments by 4, like 4, 8, C, 10 in hexadecimal, and during the decode stage, whatever addresses are to be read are given here. This is the destination register numbers, and here we have a stall cycle. We will come to that in the next slide. So we have stalls. So why do we have stalls here? If you see in the instruction, we have RI R4N and RI R2A vector, RI R3B vector, and load word R4 and 0 of R4. So there is a dependency, there is a data dependency between this instruction and this instruction. This instruction has to read R4, but this instruction has to complete writing into R4, then only this instruction can read the correct value from the R4. So when this is fetching, this is decoding. When this is fetched, and the next cycle it is decoded, and the next cycle it is executed. So there are two more cycles, which is memory access, because this accesses memory, and write backstage. So it has to wait for two more cycles before this instruction can read the actual correct value from the R4, which is why we have stalls. This type of hazard is called a data hazard, and we have introduced stalls in order to get rid of data hazard. So this program consists of a loop. So what happens exactly in a loop is, when the PC keeps on incrementing by 4, it's like you can see 5C6064. Now when it goes back, instead of incrementing by 4, it goes back to the instruction from where the loop starts. So that's how, if you see here, the PC is not after 64, it is not 68, it has gone back to the starting of the loop. So again, coming back here, when the simulation exits the loop, the PC comes to the last instruction and then keeps on incrementing. It does not go back to the instruction from where the loop starts. So here we have completed the loop, and the register R5 has the final value. The data to be written is in register 5, and what is the memory address to which we have to write the result is given by the instruction, and the memory address is 100. So that actually comes from the ALU output, where you calculate the effective address of the memory to be accessed. So the memory address is 64 in hexadecimal, which is 100. The final answer is 190 in hexadecimal, which is 400 in decimal. That is what is the expected result. And in the memory 64, which is 100, the 190 is stored. So this shows that the dot product of the two vectors is being computed properly, and it is being put in the memory address 100. The proper value of the dot product is being put in the memory address which we specified. So let's look at the next program which we ran, that is the sum of array. So here you have array with the number of elements as 8, and the array is 108327883. So what we are expecting is the sum of the array. So we have 1 plus 0 plus 8 plus 3 plus 2 plus 7 plus 8 plus 3, which is 32 in decimal, or 20 in hexadecimal. So what this does is, first it reads the number of elements which is used as a counter, and then starts reading the vector from 3. So as you can see, we have already specified that the number of elements should be in memory address 2000. So in memory address 2000 we have 8, and next we go on to actually reading the array. So the first element is read as 3, which is the first element of our array, and the array starts from memory address 5000 and proceeds forward. So this is same as the previous example, except that we don't have two arrays, we only have one array, and it enters a loop, and finally when it exits the loop, the sum is stored in memory address 1500, which is according to our instruction. So the final result is 20 in hex, which is 32 in decimal, and that is being stored in the memory address 1500, which is shown by this circle. So the next program which we ran on our Neos2 design is a factorial code. So the factorial for any number can be computed. So our example is 3, and the expected result is 3 factorial, which is 6. So the factorial uses a special type of uh, instruction called jump and link recursively, and let us see how this works in the waveform. So this is the simulation waveform for the factorial. So first we need to read the number for which we have to compute the factorial, and the expectation is that is stored in the register 10 according to our instruction. So this shows that the register 10 has the number 3 for which we have to calculate the factorial. The next instruction, specifically what I want to point out here, is the jump and link instruction. The rest of the instruction are same as the other two. So here what happens in a jump and link instruction is, the program counter, which keeps on incrementing by 4, actually does not increment by 4, but jumps to a value which is where the offset is specified by the instruction JAL. So once the JAL is done, the next instruction is storing the result in register 2. So here you can see the result is 3 factorial, which is 6, and the expectation is it is stored in register 2, which is a 32-bit register, and we have the correct value. In conclusion, we have implemented a Neos2 architecture using Verilog, and we have verified R, I, and J type of instructions. We can also include forward chaining and branch prediction for controlling hazards. And these are some of the references which we have used for this project. Thank you.